Understanding the difference in overcurrent protection requirements between Y-delta and delta-delta transformers involves examining how fault currents behave in each configuration. In a Y-delta transformer, the secondary currents, under fault conditions, do not add vectorially to zero. This is a crucial concept. Vectorial summation is a mathematical operation that takes into account both the magnitude and direction of alternating current. When a fault occurs on the secondary side of a Y-delta transformer, the resulting currents circulate in a way that the primary overcurrent protective device, or OPT, may not detect the fault quickly or effectively enough to prevent damage. This is because the fault current may not be adequately reflected on the primary side in a manner that causes the primary OPT to trip. Consequently, secondary overcurrent protection is mandated to safeguard the secondary windings, connected equipment, and personnel. The National Electrical Code, or NEC, provides specific guidelines for transformer protection, and these guidelines often necessitate secondary overcurrent protection for Y-delta configurations precisely for this reason. Conversely, in a delta-delta transformer, the secondary currents do add vectorially to zero, at least under idealized conditions. This means that if a fault occurs on the secondary side, the resulting current flow creates a corresponding current increase on the primary side that the primary OPT is designed to detect. Because the fault current is effectively reflected back to the primary side, the primary OPT is expected to trip and clear the fault, providing adequate protection. Therefore, secondary overcurrent protection is generally not required on the secondary side of a delta-delta transformer, assuming certain conditions are met, such as the transformer meeting specific impedance characteristics and the primary OPT being appropriately sized. However, it's important to note that this doesn't mean secondary protection is never used in delta-delta systems. It may be implemented for other reasons, such as protecting downstream equipment or providing selective coordination in the electrical system. To delve deeper, let's consider the implications of these configurations in real-world scenarios. Imagine a scenario in a commercial building where a 480-volt Y-grounded primary is stepping down to a 208/120-volt delta secondary. In this situation, secondary overcurrent protection is essential. If a ground fault occurs on the 208/120-volt secondary side, the fault current will circulate through the delta windings, but it may not create a large enough current imbalance on the 480-volt primary side to trip the primary breaker in a timely manner. Without secondary protection, the fault could persist, potentially leading to overheating, insulation breakdown, and even a fire. Now consider a scenario involving a delta-delta transformer in an industrial plant. This transformer is stepping down from 13.8 kV delta to 480 volts delta. If a short circuit occurs on the 480-volt secondary side, the resulting fault current will create a significant current increase on the 13.8 kV primary side. The primary overcurrent protective device, typically a circuit breaker or fuses, will detect this overcurrent and trip, interrupting the power supply and clearing the fault. Because the primary protection is expected to function effectively, secondary overcurrent protection is often omitted in this type of delta-delta configuration. The NEC Article 450 provides detailed requirements for transformer overcurrent protection. It specifies the maximum allowable overcurrent protection for transformers based on their rated voltage, impedance, and other factors. These requirements are intended to ensure that transformers are adequately protected against both overload and short-circuit conditions. When applying these requirements, it's crucial to consider the specific characteristics of the transformer and the electrical system in which it's installed. For example, if a delta-delta transformer has a relatively high impedance, the primary overcurrent protection may not provide adequate protection for secondary faults. In this case, secondary overcurrent protection may be necessary to supplement the primary protection. Furthermore, the NEC distinguishes between different types of transformer connections, such as single-phase, three-phase, and auto-transformers, and it provides specific overcurrent protection requirements for each type. It also addresses the use of different types of overcurrent protective devices, such as circuit breakers, fuses, and ground fault protection devices. Selecting the appropriate type and size of overcurrent protective device is essential for ensuring that the transformer is adequately protected. In addition to the NEC requirements, there are also industry standards and best practices for transformer overcurrent protection. These standards provide guidance on topics such as coordination of overcurrent protective devices, selection of appropriate protection schemes, and testing and maintenance of overcurrent protection systems. Following these standards can help to improve the reliability and safety of transformer installations. Coordination of overcurrent protective devices involves selecting and setting the devices so that they operate in a coordinated manner. This means that the device closest to the fault should trip first, while the upstream devices remain closed. This helps to minimize the extent of the outage and prevent unnecessary tripping of upstream devices. Selective coordination is a particularly important consideration in critical applications such as hospitals and data centers, where even a brief power outage can have significant consequences. Different protection schemes can be used for transformer overcurrent protection, depending on the specific application and the level of protection required. Some common protection schemes include overcurrent protection, differential protection, and restricted earth fault protection. Overcurrent protection is the most basic type of protection, and it provides protection against overloads and short circuits. Differential protection is a more sophisticated type of protection that provides protection against internal faults within the transformer windings. Restricted earth fault protection provides protection against ground faults within the transformer windings. Testing and maintenance of overcurrent protection systems are essential for ensuring that the systems are functioning properly. Testing should be performed periodically to verify that the overcurrent protective devices are operating correctly and that the settings are appropriate. Maintenance should be performed to keep the devices clean and free from corrosion. Let's elaborate on the vectorial summation concept. In a balanced three-phase system, the three phases are 120 electrical degrees apart. In a delta-connected system, the line current is the vector sum of the currents in two of the phases. Under normal operating conditions, these currents add vectorially to zero, meaning that the net current flow is zero. However, when a fault occurs, this balance is disrupted, and the currents no longer add to zero. In a delta-delta transformer, the circulating currents within the delta windings can help to mitigate the effects of a fault. However, in a Y-delta transformer, the Y connection on the primary side does not provide the same level of fault current mitigation. This is why secondary overcurrent protection is generally required for Y-delta transformers. Now, let's consider the impact of transformer impedance on overcurrent protection. Transformer impedance is a measure of the transformer's opposition to the flow of alternating current. A higher impedance transformer will limit the fault current to a greater extent than a lower impedance transformer. This means that the primary overcurrent protection may not provide adequate protection for secondary faults in a high impedance transformer. In this case, secondary overcurrent protection may be necessary to supplement the primary protection. The percentage impedance of a transformer is an important factor in determining the appropriate overcurrent protection. The percentage impedance is defined as the voltage drop across the transformer at rated current, expressed as a percentage of the rated voltage. A typical percentage impedance for a transformer is between 5% and 10%. The NEC provides guidelines for selecting the appropriate overcurrent protection based on the transformer's percentage impedance. In addition to the percentage impedance, the transformer's kVA rating is also an important factor in determining the appropriate overcurrent protection. The kVA rating is a measure of the transformer's apparent power capacity. A higher kVA transformer will require a higher rated overcurrent protective device. The NEC provides tables that specify the maximum allowable overcurrent protection for transformers based on their kVA rating. When selecting overcurrent protection for a transformer, it's important to consider the transformer's inrush current. Inrush current is the high current that flows when a transformer is initially energized. The inrush current can be several times the transformer's rated current, and it can last for several cycles. If the overcurrent protection is not properly sized, it can trip during the inrush current, causing an unnecessary outage. To avoid nuisance tripping, it's important to select an overcurrent protective device that can withstand the transformer's inrush current. Time delay fuses or circuit breakers with adjustable instantaneous trip settings can be used to provide this capability. Furthermore, it's important to consider the transformer's operating environment when selecting overcurrent protection. The operating environment could affect the performance of the overcurrent protective devices. For example, high temperatures can cause the devices to direct, while corrosive environments can damage the devices. When selecting overcurrent protection for a harsh environment, it's important to choose devices that are specifically designed for that environment. Surge protection is another important consideration for transformer protection. Surges are transient overvoltages that can damage transformers and other electrical equipment. Surges can be caused by lightning strikes, switching operations, and other events. Surge protective devices, or SPDs, can be used to protect transformers from surges. SPD are typically installed at the transformer's primary and secondary terminals. In addition to overcurrent protection and surge protection, it's also important to consider grounding when protecting transformers. Grounding provides a path for fault current to flow back to the source, which helps to clear the fault and protect equipment and personnel. The NEC provides detailed requirements for grounding transformers. These requirements specify the size and type of grounding conductors, as well as the location of the grounding electrodes. Proper grounding is essential for ensuring the safety and reliability of transformer installations. One final consideration is the maintenance of transformer overcurrent protection systems. Regular maintenance is essential for ensuring that the systems are functioning properly. Maintenance should include visual inspection of the overcurrent protective devices, testing of the devices, and cleaning of the devices. Testing should be performed periodically to verify that the overcurrent protective devices are operating correctly and that the settings are appropriate. Cleaning should be performed to remove dirt, dust, and other contaminants that can affect the performance of the devices. By following these best practices for transformer overcurrent protection, you can help to ensure the safety and reliability of your electrical system. Remember that secondary protection might still be desirable even on delta-delta banks where downstream equipment may require a closer level of protection to protect smaller conductors, motors, or components from fault currents that the primary protection might not catch quick enough.